Did you find a way to record it?
Well, I think we have.
Okay.
At least one, maybe two ways to record it. Yeah.
Certainly different perspectives.
How about that? Yeah, it does. Oh, yeah, it moves.
You want a better spot or something?
It's fine the way it is.
We're finally doing this number that we've been trying to get everybody together for.
Can we maybe sit down and get started pretty soon?
Nah.
Don't start too late.
That's a good point to make.
It's one of our fancy calendars.
Oh, for the Solar Observatory?
Mm-hmm. Yes, this year we have fancy calendars.
Well, good afternoon and welcome. My name is Claude Flymate. I'm the engineer and chief observer for the Big Bear Solar Observatory. Our director, Sasha Kosovicha, was unable to be here today, so he's asked me to stand in for him. So please put up with me for the short duration. One thing he definitely wanted me to comment on and let you know about is our friends of the Big Bear Observatory organization. Big Bear BBSO is quite committed to trying to increase our presence here in the Big Bear community. That's evidenced by our partnership here at the Discovery Center, the projects we're doing with the local schools, this very visible lecture series, and this new fledgling organization. This is an idea to increase our interaction with the local public. If you join, I know you get a BBSO calendar. If you'd like to find out more about the Friends of the BBSO, you should speak with Erica in the back of the room. Thanks, Erica. Now, this is the second talk in the BBSO public lecture series. Today, we're very pleased to have our own John Varsik speaking to us on the history of the BBSO, the Big Bear Solar Observatory. Let me see if I get this correct. John received his PhD at the University of Hawaii, and correct me if I'm wrong, John, since then, for the past 26 years, he's been working in the field of solar astronomy, both here with the Big Bear Solar Observatory and at the National Solar Observatory in Sacramento Peak, New Mexico. John certainly wears many hats here at our observatory. He's responsible for our information technologies. He personally developed much of the telescope control software for the facility. He writes the observatory's daily solar activity forecast, and in his spare time he's known to operate the telescopes as well. John has seen several generations of instrumentation and personnel come through the observatory here. There's really no one more qualified to talk about the observatory from a historical perspective. Please welcome Dr. John Varsik.
Well, thank you, Claude. Just wanted to say, you know, when you're in Big Bear, you can go to the Historical Society and you hear all sorts of interesting talks about all sorts of strange things like grizzly bears and dams and fox farms and all sorts of odd things, but usually you don't hear much about solar observatories. And it's kind of a shame because we're very fortunate here in Big Bear. We have this facility which is one of the major solar observatories in the world. And it'd be really pleasant if more people were aware of what we're doing and maybe have a little appreciation for what this place can do for the study of our nearest star. I'm going to be spending most of my time today not talking about solar astronomy or about the sun in particular, but about solar telescopes and solar instrumentation and why we ended up here in Big Bear. Big Bear Solar Observatory was dedicated in 1970, but the story goes back quite a bit further than that. It was originally founded by Caltech, California Institute of Technology. It's now operated by NJIT, New Jersey Institute of Technology. And we're now operating what we can think of as the highest resolution solar telescope in the world, which we call NST. But the story goes back further than that. The sun is a typical star, and the reason why we're interested in it, basically, is that the sun is more or less the Rosetta Stone of astrophysics. The sun allows us to get a good close-up view of the surface of an actual star. The other stars are up hundreds of thousands of times further away at minimum. But by looking at the sun, we can understand in great detail what's happening on the surface of a fairly ordinary star. Solar activity also affects our technology and our lives in various ways, but here again, that's not really the subject of this talk. Briefly though, there are some details about the structure of the sun that are of some importance. Basically, when we're looking at from the surface of the ground, the surface of the Earth, we're able to study the lower levels of the solar atmosphere pretty well. The photosphere, the normally visible surface, the area of the temperature minimum, the top of the photosphere, bottom of the chromosphere, the next layer up. What we don't get a good view of from the ground in general is the corona. The corona can only be seen from the ground under very limited circumstances, either during rare solar eclipses or from very few high altitude sites, higher than Big Bear, that can operate instruments called coronagraphs. But what we are able to do is we can measure the magnetic fields on the sun, which can tell us a great deal about solar activity, about how sunspots form, how solar flares form, and how these active regions develop on the sun. And people have been doing this sort of work for quite some time. Now, Galileo was the first person to observe the sun with a telescope back in 1609. And he was using a very primitive telescope and some slightly dangerous techniques. But it wasn't long after that before much better techniques were developed. This is a drawing of a telescope from about 1630. And it shows a technique of observing the sun, which is not very different from what a lot of amateur astronomers do today. You have a small telescope up here. It's mounted on this stick, and it's set up to project an image of the sun onto this easel back here. And it even is mounted on this mount here, which allows it to track the sun with one motion. And it's the same kind of mount we use today. And in fact, many astronomers still observe the sun in the same way. For example, this is a drawing from probably the best place for solar drawings in the world, which is the Mount Wilson Observatory, from a couple days ago. And you can see all the sunspots that were on the disk at that time. Now at Mount Wilson, they also have a setup feeding a spectrograph, which allows them actually to measure visually the magnetic fields of the sunspot umbra, which is what a lot of these numbers are that are next to the sunspots. Okay, so going back again, the sun gives us an active changing star we can get a good look at. And what happened roughly 150 years ago, starting 150 years ago, was that this technique called spectroscopy began to be developed. And what spectroscopy allows us to do is split the light of the sun, or of stars, up into a spectrum of the rainbow. And if you split it up wide enough, what you'll notice is, or what you find is that the individual colors can be associated, many of them can be associated with emission or absorption from individual atoms that are in the surface of the sun or the star that you're looking at. And this technique is what allows us to understand what the sun and stars are made of and how they work. But this technique, because it spreads out the light so much, it began to be a problem. You couldn't photograph it very well because it made things rather faint, even with the sun. And so around 100 years ago, it began to be realized it was important to have large telescopes that were specially built to look at the sun. And the first person really to do this on a regular basis was a fellow named George Hale, who was a great solar observer and telescope maker. And he's associated, in fact, with the establishment of many observatories in the United States, including Yerkes Observatory, which is owned by the University of Chicago and is in Wisconsin. And then when he realized that the observing conditions in Wisconsin weren't all that wonderful, he came out to California and found that things were much better out here. And he went on to establish two great observatories for observing not only the sun but also nighttime objects, and these are Mount Wilson and Palomar. And he was also instrumental in making the California Institute of Technology the great institution that it is today. So, starting in 1904, so 110 years ago, he began to build a series of solar telescopes at Mount Wilson. And the first one he built was known as the Snow Telescope, and it's this thing here. And it has a flat mirror out here that directs the sunlight into a horizontal telescope and into a spectrograph further back. What he found when he did that was that the great nemesis of all solar astronomers, which is that the sun is hot and it heats up the ground. And when it heats up the ground, the air above the ground begins to convect and it distorts the images. And this produces what the astronomers call bad seeing. Okay. And the sun's very good at this. And so in general, most places, daytime seeing is much worse than seeing at night. So Hale began to think of, well, what can we do to defeat this problem? And in fact, trying to deal with or defeat this problem has been one of the great themes of solar telescopes for the last 100 years. And what Hale did was he took a small telescope and started climbing around in trees on Mount Wilson. And what he found is that it seemed like the seeing was better if he climbed up further in the tree. So what he said, okay, let's build a telescope on a tower. Okay? And so this is what he tried to do next. He built this thing out here. This is called the 60-foot tower telescope. And it consists of this tower with some flat mirrors in the top and a telescope lens in the top that focuses the light down into an observing room down at ground level. And the idea was you could get the telescope above the ground and avoid some of the problems of the sun heating the ground. And it sort of worked. And so I thought, well, we'll build a taller tower. So he built a 150-foot tower, which is this thing in the back, and you can see there's a better picture of it here. And these tower telescopes did work up to a point in reducing the effects of the solar ground heating. However, even at that point, the solar ground heating would eventually warm up the ground, and after a couple hours or so in the morning, the conditions at Mount Wilson are usually not very good. It's not a bad thing to say about Wilson. Conditions almost everywhere when you observe the sun after it's been up for a couple hours aren't very good. These telescopes, the 60-foot tower and the 150-foot tower, are still in use today, although I'm not sure for how much longer. Well, of course, Mount Wilson was operated, and Palomar were operated by Caltech, and Caltech had a big solar astronomy department. By the 1960s, the active nature of the sun, the evolution of what we call active regions, the sunspot areas, and the production of solar flares was under intensive study. Part of this had to do with the advent of the space program. The space program allowed us to put satellites in orbit that were actually measuring the solar wind and other emissions from the sun. And in order to understand where these things are coming from, we needed to have a better idea of how active regions evolved over time. And so the advent of narrow band filters, which had been invented back in the 30s, and stop motion cameras allowed the study of these rapidly changing solar features. But there was a big catch. You couldn't do it very well from Mount Wilson because after a couple hours in the morning, the seeing got bad and you couldn't see anything. So the Caltech Solar Group decided, well, let's try to build a new observatory that we will carefully select a site that has the best possible conditions. Okay. And so they decided, okay, we will conduct a great survey of places all over Southern California to find the best spot. Now, back in the 1950s, meanwhile, in Germany, Karl Kiepenheuer, who was at the Fraunhofer Institute, what was then the Fraunhofer Institute in Freiburg, which was kind of the Germans' big solar astronomy institute, still is, advocated placing solar telescopes near water. The idea was that the water has a high heat capacity, it reduces the amount of convection in the air above the water, so the images should be more stable. And Kiepenheuer and his group built a telescope on the island of Capri, off the coast of Italy, and found that it did work up to a point. And so the Caltech group decided that, okay, we will add some lake and ocean sites to the survey just to check this idea out. So they had some criteria for the selection of their new observatory. It had to be within 125 miles or so of Pasadena so they could get to it, okay? And it had to be someplace that was reasonably accessible because they didn't want to have to spend all the money to build a road, okay? And they had to be able to buy land so they could build the place. And they wanted a place that had long periods of good seeing so that they could make their time-lapse movies. And other factors that they included in their selection was they wanted to also the site to have good transparency, which means that it's free of haze and smog and dust and so forth. These are things that don't necessarily distort the image, but reduce the contrast. And they also wanted a place that was reasonably clear and didn't have a lot of low clouds and fog. So they started off with starting with an 8-inch reflecting telescope that they put in the back of a truck and went around to a number of different locations. And they started with 34 sites and 100 locations, slightly different locations at those different sites around Southern California. And this was taking place in 1966 and 1967. Okay. And then finally, they did some observations using a portable narrowband solar telescope, which we call the Carroll Spar, and they finally did those final observations at Big Bear and Lake Elsinore. This is what the Carroll Spar telescope looks like. We had this telescope at Big Bear for many years after the survey was completed. As I understand it right now, it's kind of in storage at Mount Wilson. I think that's the last place it was at. And it could still be put back into service. But anyway, so these are the locations that were picked. And you can see there's a big variety of sites, everywhere from Catalina Island to Gaviota near Santa Barbara, Mount Pinos, Palomar, Big Bear, the Caltech campus, all these other places. Look, Lake Elsinore is over here. And so what did they find? Well, these are some of the results from that survey. Okay, and let me show you what these are. These are the seeing values rated from 0 to 10 on a scale. And this is local time. Okay, and this is, so we have Lake Elsinore, you have the Refugio Beach, that's near Santa Barbara, Caltech campus, Big Bear, and so forth. Okay, and what you find is that typically, this, like for example, here at Lake Elsinore, the seeing will peak sometime in the morning, and then it deteriorates. What you'll notice about Big Bear is that it stays reasonably good all day. And the same was more or less true of Lake Elsinore. And so what they ended up doing is they finally narrowed it down to choosing between Lake Elsinore and Big Bear. When the seeing was better, as you could see from that chart, from their survey at Lake Elsinore. But Lake Elsinore is, it's relatively low altitude, and they get a lot of low clouds and fog there, okay? And which we don't get here. And so that's what led to the choice of the Big Bear site. Now it's interesting to note that most of the site survey observations for Big Bear were actually taken at a place called Moon Camp, which is just west of the observatory heading towards Fawnskin. Okay? In fact, as I understand it, right now there's some kind of project to build something there, but at the moment right now it's still empty. But Caltech was able to buy the land just east of there at the observatory site. What they found is that once the observatory was built, in fact, what they found is that the seeing, the stability of the air out on the lake was even much better than what they had found at the shoreline. Remember that the site survey data were actually taken at the shoreline, not out on the middle of the lake where the observatory is. Okay. So the survey was primarily put into motion by Robert Layton, who was one of the main people at the Caltech astronomy department. And he hired a fellow named Hal Zirin, who came to Caltech in 1965, and Layton put him in charge of building the observatory. And the onshore land was bought by Caltech, and the observatory site was leased from Bear Valley Mutual, which is the people who owned the lake bottom. And so in 1968, they began construction at the observatory site. And what you'll notice, a couple things right away you'll notice about this. One thing, the lake was very low. Okay, the lake was very low. Yeah, you have to remember in those days, the lake was being run by Bear Valley Mutual, and it was being run for irrigation and down in Redlands. And so very often the lake was drawn down quite a bit in order to water the orange groves. And so this was not unusual at the time. And what you notice is that there's this slightly higher point out here, and they built up this road which goes out there. Now, in fact, what you're seeing here is not the causeway that's there now. It's quite a bit lower than the causeway that's there now. And so later on, in 1968, they began building the observatory building, which you can see here. And then there came the winter. And the winter of 1968 was an extremely wet winter. And it was one of the wettest winters that we've ever had here. And they had like 25 inches of rain. Now that's rain, mind you. So what happened? The lake filled up. Okay. Well, fortunately, the observatory building was built to handle that. And what you'll notice is that there's this area here. This is actually the floor below the ground level that's there now. And so the lake wasn't quite full. And this area here is the entrance where you normally go into the building now. You also notice that the dome wasn't there. They had a plywood roof on top of the building. Here it is in early '69. Now, interesting thing here is that, for one thing, it's very wet again. You'll see that they're starting to put the dome on. Okay? You'll see that the lake water level is close to the top, and that there's this little dome here. This is where the final site survey measurements were taken. And the foundation for this dome is still out there at the observatory. It's hidden under a giant willow tree, but it's still out there. Now, when the observatory was finished in 1970, we have the first set of telescopes. There have been 3 sets of telescopes in the dome over the years. And this is the inventory of the first set of telescopes. Okay? And there was a large tube in the dome, and inside the large tube were 2 10-inch refractors and a 16-inch reflecting telescope to feed the spectrograph, and a rather odd instrument for the time, a 9-inch reflecting coronagraph. Now, a coronagraph, again, is an instrument for trying to observe the solar corona from the ground. And normally coronagraphs are found at higher altitude sites than Big Bear, and there's a good reason for that, which is that at higher altitudes than Big Bear in general, you have less scattered light and you can actually see the corona. But Zirin was not afraid to try new things, and not only was he trying to use a coronagraph at Big Bear, which is a pretty low site to use a coronagraph, but he was building a reflecting coronagraph, which as far as I know hadn't been tried before. And most coronagraphs are built with very carefully selected lenses. It turns out that lenses scatter less light than mirrors do. And but Zirin was trying this new technique of a reflecting coronagraph. It never worked out. It never really worked right. Shortly after the observatory was finished, an additional telescope was put on top of this big tube, which was a hydrogen alpha telescope, which was designed for training the Skylab astronauts, who, in addition to being in the space station, the Skylab space station in the early 70s, were also going to be solar observers, because the Skylab space station had this wonderful solar observatory attached to it. And so the astronauts had to learn how to observe the sun. Here's a diagram of the inside of that telescope, and you can see here's the front end of it with this off-axis 16-inch telescope to feed the spectrograph and so forth. Now, and this was all put in for the first series of instruments. And you'll notice that the spectrograph was built in the floor below, and it's in this big round tank which rotates to correct for the rotation of the image. Very quickly, a new instrument was added to this setup, known as the video magnetograph, which allowed for magnetic field measurements to be made. And this not only allowed magnetic field measurements to be made, but the changes in the magnetic fields during the day could be tracked, which had never been possible before. Because magnetographs before this time had all been based on spectrographs, which took a long time to build up a magnetic field image. So here's a picture of the first. This is the same telescope as in that drawing. This is when this was down at Caltech. They installed the telescope on the roof of one of the buildings down there to test it out before they brought it to Big Bear. And this is the reason why I picked this picture is that it turns out there are very few pictures of this telescope that exist. And this is one of them. This is one of the other ones that exists. And this is at Big Bear in the old dome. And you can see the time-lapse movie cameras mounted on the back. These are being fed by the 2-inch 10-inch refractors. 2 10-inch refractors. Here are some images from that telescope. You see, this is a nice prominence here, and a very famous solar flare from 1972. Now, in 1973, all those telescopes were pulled out. Zirin was not happy with the off-axis chronograph, which never worked. Also, the off-axis Cassegrain telescope to feed the spectrograph never worked very well either, and he wanted to get something better. And so it turns out that during this time he had also been involved with this project for building an additional solar telescope which was planned to be flown on the second Skylab space station, which of course none of you have ever heard of because it never flew. However, the telescope was built and it ended up at Big Bear. And so this big tank here has that telescope inside it. Now, of course, that telescope was designed to fly in space, and it was built in a vacuum tank with a big window on the front for use at Big Bear. And now it turns out that putting a solar telescope in a vacuum tank is a really good idea, because not only do you have to worry about the sun heating up the ground and causing convection currents in the air above the ground, you also have to worry about the sun heating up the air in the telescope, and heating up the mirror in the telescope, and heating up the air above the mirror, and it gets convection currents inside the telescope, which is just as bad a problem as is a worse problem than having them elsewhere. And so by putting the telescope in a big vacuum tank, you avoid that problem. Okay? Makes it a lot harder to work on the telescope, but it does produce better images.
Excuse me, John.
Yes?
Question. With the input window on the vacuum tank, they're concerned about hitting the input window with the converging solar beam. Were you?
Well, the internal. Actually, no. The internal geometry of the telescope, it's what we call a Gregorian telescope. And so at the bottom of the tank, there's a 26-inch mirror down here, or there was, and it focused the light inside the tank onto this thing called the heat stop. Now, of course, when you're moving the telescope onto the sun, that beam is not going to be hitting the heat stop necessarily, but it turns out that beam is also diverging before it hits the window, and so yeah, that was not a problem. Yeah. And so here's another view of that telescope. You have the back. This is the back of the tank. You're looking along the side of the telescope, and this is the back of the 10-inch telescope. Now, of course, what happened was that you ended up not only with this 26-inch vacuum telescope, but Zirin also kept one of the 10-inch telescopes, and the hydrogen alpha full disk telescope, the so-called Singer-Link telescope, and he slung those underneath the vacuum telescope. At the back of the 10-inch telescope, there was a set of flip mirrors to send the light to 3 different cameras in sequence. So the mirrors would flip in and out. And usually you ran with a hydrogen alpha filter on one side and say a calcium K-line filter on the other side. And those would be run with the stop motion movie cameras. And then in the middle of the array was the magnetograph instrument. And here's another view. This is the front end of the 26-inch telescope. And there was this cooling ring mounted on the front. And the idea of that was you could run cool water through here. And that would keep the air above the entrance window, which is here, from getting hot. Okay. And this is all controlled from this rather big, complicated, scary-looking control panel that was up in the dome with the telescope. Okay. And so this, I'm not going to explain all the things about this panel, but you have the controls for moving the telescope, you have the controls for controlling the flip mirrors, you have exposure meters for the cameras, you have guider amplifiers here, you have the video outputs here. This picture was from 1991. By then, in addition to the film cameras that were being used on most of the filters, there are also time-lapse video cameras that were being used. The reason for that was, well, there were a couple reasons for that. One was that it allowed for the data to be reviewed quickly because you didn't have to wait for it to be processed. And the other was you could more easily control the time-lapse sequences and so forth with the video. The bad part about that was that the video was pretty low resolution. And of course the film was much better. But we used a lot of video at that time. Anyway, but as you can see, the images from the 26-inch telescope under very good atmospheric conditions could be quite good. Now, one thing about solar seeing is that even at a site like Big Bear, it's extremely rare for conditions to be stable enough so that the atmosphere will be, that you'll be able to get the full resolution from a telescope of that size. In fact, that hardly ever happens. In general, the best conditions that you'll see at Big Bear will allow you to get full resolution, say, from the 10-inch refractors, but not from anything larger than that. As we would say, the Freed parameter is something at best is like 25 centimeters in technical terms. But here's another view. You can see again that you can get reasonably good images of the penumbra of the sunspot. Now, one of our main missions, of course, was to do these time-lapse movies, and so this is an example of one of them. This was transferred to video many years ago, and so in the background you can hear the clock running, which has nothing to do with the video. And so you can see the solar flare here. This flare is from 1989, which was a peak year of solar activity.
23 hours.
Yeah. That isn't when it was taken. And now we've changed wavelengths. So it's like that. Here's another one. And so here now we've changed position and we've changed the exposure so that we can get more of the detail of the active prominence. Anyway, that's the sort of thing that we were getting. So, as some of you may remember, in 1992 we had this little earthquake, June 28th, and that caused quite a bit of damage at the observatory. What happened primarily was that the concrete pier that the telescope was mounted on split down the middle. and almost, if it had been shaking, I think, for 5 or 10 seconds longer, the whole thing would have come apart, and the telescope would have ended up going through the floor. But as it was, the whole pier had to be cut down and replaced. And so the telescope was taken out of the dome and put on a truck and put in the garage that we have on shore. And the whole pier was replaced with a new one. And we were out of action for about 4 months. And another thing that happened that was interesting happened in the 90s was that Big Bear became attached to a wider world of solar observing. We became associated with what's known as the GONG program. GONG telescope is actually mounted in this innocuous-looking shipping container that's parked at the shoreline at the observatory. And there's actually a telescope in there that runs automatically and tracks the sun. It turns out that what it's doing is it's observing the solar vibrations. The sun vibrates like a big bell at a very low frequency. Normally audible sound is between 20 cycles per second and 20,000 cycles per second. But these solar frequencies, these solar oscillations occurring are at cycles of anywhere between 1 cycle every 3 minutes to 1 cycle every 5 minutes or so. And so it vibrates at these very low frequencies. Now, the interesting thing about that is that you can measure how these vibrations are propagating through the interior of the sun, which can tell us about the interior structure of the sun in ways that are otherwise completely impossible to do. So the GONG instrument allows us to do this. And it does this by having 6 identical telescopes spaced around the planet, so that when the sun goes down in Big Bear, it's still up in Hawaii and in Australia, and then later on in India and in the Canary Islands and in Chile. And so as the Earth rotates, the sun is always shining down on at least one of the GONG telescopes. And the raw data from the GONG telescope look like this. So you're seeing all of the gas moving up and down in the surface of the sun. Okay? And so by slicing out the frequencies spatially and temporally of the vibrations in images like this, you're able to map the interior of the sun. It's quite a complicated process, and it involves taking very long sequences of these kinds of images, which is why you need the multiple telescopes, so that you're not interrupted by nighttime or by clouds. Before the telescopes were set up at their various locations, they were all tested all together in Tucson, a place that they called the Gong Farm, because they were growing gongs. And the sunlight is fed into the telescope through this turret, which tracks the sun automatically, and is fed into a very narrowband filter system here and into the camera system, which is inside this can. Now, in 1997, Professor Zirin retired, and at that point, Caltech decided that they wanted to concentrate more of their effort on their nighttime programs. During this time, the Caltech had not only, for all this time they'd had Palomar, and now they had developed the Keck telescopes in Hawaii, and they were working on all these other nighttime projects, and so they decided that it would be better to concentrate their efforts there and get out of the solar astronomy business. But they had the good sense to realize that Big Bear was a really good observatory, and rather than just shutting us down, they decided to see if some other institution could be brought in to operate the observatory. And so NJIT had a good solar astronomy group with a number of former Caltech people, and they agreed to take over the operation. And so now the observatory is now operated by NJIT. And so things continued for a number of years after that, gradually replacing the film cameras and the video cameras with digital cameras, and improving the instrumentation, and replacing the single spectrograph that we had for many years as our single Coude instrument, with a whole Coude laboratory with optical benches and so forth inside, so that a variety of different kinds of instruments could be operated in a fixed location, which is much easier to operate than having the instruments hanging on the telescope. But still, it came down to a question of how viable the telescope was going to remain into the future. People realized by then that space-based observatories were becoming possible and were going to be built, and that once you had, say, a half-meter solar telescope in orbit, then it would produce perfect images all the time, because there's no atmosphere up there, and so there's no distortion of the image at all. And so, how are we going to keep operating? How are we going to compete with that? Well, there were a couple of things that would help us. The first thing is that, of course, being on the ground, it's possible to build a big telescope without spending a huge amount of money. The Hubble telescope is a 2-meter telescope, and it cost something like $1 billion or something, or more than that. And of course, it can't be used on the sun, but you could, in principle, build a big telescope like that just for the sun. But there were two things wrong with that. One is that the money was never going to be available, and that the solar community just wasn't big enough to push for a project like that. But you could build big telescopes on the ground for relatively little money. Unfortunately, you have to deal with the distortion. But there was a way around that. About 20 years before that, back in the late 70s, early 80s, the Air Force had begun developing this technique called adaptive optics, which basically lets you measure the distortion very rapidly and insert an opposite distortion into the optical path and correct for it. And so by doing that, you could, in principle at least, have a perfect solar image no matter what size telescope you had. And so it began to be possible then to think about building a bigger telescope. And if we built a bigger telescope, then we could observe at higher resolution than the spacecraft can, and for less money, and keep operating. And so after many years, such a telescope has actually been built. And in 2008, we have installed, it says the world's biggest aperture telescope. I'm going to get in a lot of trouble with this. I'm not going to go there. Anyway, it turns out there is another telescope in Arizona, which is just about the same size as this one.
Smaller.
It depends how you look at it. It's slightly smaller, but not enough to matter. But the thing is that telescope has never had really high-resolution images because it wasn't built for adaptive optics. It was built many years ago. And it has a lot of internal seeing problems, as well as being on the top of a hot mountain with no lake around it. But anyway, so we have built this 1.6 meter solar telescope, which is optimized for high resolution imaging and adaptive optics. So in 2003, we began to have the mirror made. This is a picture of the mirroring rough ground at the old, what was then Kodak plant in New York. The mirror itself is made of a material called Zero-Dur, which is from Germany. And the property of this particular kind of glass is that it changes its shape very little with temperature. It's kind of like a super-duper Pyrex. And so even though it may get warm with the sunlight shining on it, it doesn't change shape, which means the focus doesn't change. And so finally, in 2008, the telescope was installed. We have a new dome now. because the telescope was too big to fit in the old dome. And here it is. You notice it has some unusual features for a telescope of this size. It has this is the main part of the structure here. The telescope is pointed this way up through that hole. But you'll notice that the main mirror at the back is tilted. Okay? And this is because it's what's called an off-axis mirror. Instead of having the focus in front of the mirror, the way a normal telescope does, it has the focus off to the side, which having the focus in front of the primary mirror reduces the contrast. And it also makes it harder for the adaptive optics to work. And so in order to prevent those problems, the telescope was built with this off-axis configuration. Now this again was not the first time that such a telescope had been built. William Herschel built off-axis telescopes 200 years ago. But his telescopes and all off-axis telescopes since then were extremely long focal length. This telescope has a very short focal length. It's about f2.5 if I remember right. And so for its diameter, it's a very short focal length. And it's extremely off-axis. So that in fact, you can think of it as being a section out of a theoretical mirror, an on-axis mirror of about this size. Okay, and so it's extremely off-axis, and grinding, polishing and figuring such a mirror was a big challenge, and it had never been done before with a mirror this far off-axis of this size. Here's another picture of the telescope in the dome. Sometimes we have to do work on the outside of the telescope when we hire a big man lift to do that, and we can take pictures like this. We can't do this normally. Okay. And then here is what the telescope looks like when it's pointed at the sun. Okay. The light is being focused out over here, behind this bar here, so you can't see it. And this is actually the primary mirror right here. Now, the telescope is not just, when we think of the telescope, it's not really right to think of just the telescope as the thing that's up in the top of the dome and moving around. The telescope is the whole set of instrumentation. So you have the thing on the top of the dome that's moving around, that's this part up here, and it focuses the light down to flat mirrors inside here, which send the light down here, down the axis. And then down into these laboratories down below. These are the descendants of the Coude spectrograph. This is where all of the science cameras are, and where the adaptive optics system is located. And so we can work on these things down in a fixed laboratory at a fixed temperature, which makes things simpler for maintaining those instruments. But it does require having this complicated optical system to get the light down there. And this is what the inside of the laboratory looks like. You can see some of the light bouncing off some of the mirrors inside. And it actually works, which is the remarkable thing. So here is the proof of the pudding. Okay? These are two images of the same location of the sun at just about exactly the same time, taken with Hinode, which is a spacecraft with a half-meter mirror, a very fine instrument in space, and with the NST. So it's the same scale, you can see the same features here, but in our image you can see the details that you can't see with the spacecraft. And that's the whole reason for doing this. So here's a picture of a sunspot. Nice, ordinary, round sunspot. You can think of this picture and compare it with the one from 1989 from the 26-inch. Similar features, but you can see much finer details here that were impossible to see with earlier generation telescopes.
Can you give an idea of scale for this?
Well, let's see. Let me give an idea of the scale. These features on the outside of the sunspot are called solar granulation. And each of these features is roughly the size, say, of California. More or less. Okay? And so you can see that the sunspot it's bigger than the Earth. And so, going back to the original purpose of the observatory at Big Bear, which was to make time-lapse movies of the evolution of solar activity, here's what we can do now.
Is that like a plasma, would you call it?
Oh yes,
Kinda like
yes. So this is the solar granulation, and what you're seeing, it's like if you're looking down at, all right, if you can think of I mean, this is gas, okay, but think of it, if you think of it as like liquid, you can think of it as like a pot of boiling water, okay? You have the heat coming up from the bottom, you have these convective cells coming up to the top and expanding and going back down. That's what's happening here. And what the interesting thing is are these small features at the edges of the granules, which have not been well observed before. And that's something that we're working on. We can also see how, in this case, new magnetic flux emerges near a sunspot. The sunspot is over here. You can see the granulation here, but you'll notice here that there's kind of this odd-shaped granulation here. And if we watch the movie, you'll see how things are emerging here. You can see these loop structures appearing and spreading out. That's tracing the magnetic field structures coming out near the sunspot. We can also look at the center of hydrogen alpha. This is not a really great movie, but it's what I had at the moment. This is I should replace this. But anyway, you get an idea of what's happening here. This is from like 2009 or something. So we have better ones now.
John, what's the frame rate for this?
Well, this image, it's covering about half an hour, I think. No, this one, let me see here. More like 10 minutes. 10 minutes.
10 seconds.
No, so the frame rate is probably about one image every 10 seconds. Okay. But this image from 2012 this is probably one of our more remarkable movies so far. So what we have here again, this is a sunspot, okay, and now we're kind of in what we call the wing of the hydrogen alpha line. We're a little bit off of the center of the line, which allows us to see the photospheric features pretty well, but also gives us a good view of the some of the chromospheric features here. Now this is another time-lapse movie. And you'll see a couple of small solar flares taking place here. And so this is what we are working on now, and we're continuing to improve our imaging capability, and we're trying to better understand what's happening in these films. A lot of these features are things that haven't really been seen before, and so understanding exactly what they are is going to take a little time.
Why is this in black and white?
Well, most of our films, well, all of our movies are black and white because we're looking in one particular wavelength. Okay, so we're looking at hydrogen alpha, say, which is a particular color of red. Okay, and so everything is that color. Okay, it turns out that when you have a digital camera, that you can get a higher resolution, better performing camera if it's a black and white camera than if it's a color camera. And so since everything is all the same color anyway, it doesn't matter. And so a lot of times when you see films that are released for the public, they will be colorized. Okay? And so they will put the color back in later. Okay, but in fact, the original data are black and white like this. Okay.
How
So
narrow is the wavelength? Would it be like 1 micron or more?
this one,
Yeah.
this is at hydrogen alpha, so it's 653. Yeah, 656 nanometers, or 65, 63 angstroms. It's a deep red color. Okay.
John, this movie was taken in 30.
Oh, this is 10830? Oh,
Black blue.
okay. Well, then it is infrared. Okay.
The black blue says something nobody ever seen before.
Ah, this is 10830. Okay. Well, 10830 is an interesting line. It's a helium line in the infrared. Infrared is good for us because it turns out that the distortion from the atmosphere is less in the infrared, and the adaptive optics works better. So, all right. So it's not H alpha. I'll have to fix that. All right, well, that's all I have for today. And if you have any questions, I'll be happy to try to answer them.
What's next?
Okay.
What's the next step in evolution?
Well, the next step in the evolution of the observatory is a new instrument we're building called SIRA. And SIRA is a infrared spectrograph that's intended to work at wavelengths that are longer than what we've been able to work at before. It will be working in the range between 2 and 5 microns. Now, it turns out that there are some interesting solar features in that wavelength range that have only been able to be investigated from a couple of other observatories and not at the resolution that we hope to be able to get. They will enable us to look at details of the layer of the solar atmosphere immediately above the photosphere, what we call the temperature minimum, and try to look at more detail about how the solar atmosphere transforms from being dominated by the motions of the gas to being dominated by the motions of the magnetic fields. So that there are regions at the temperature minimum which are relatively cool, which should show up well in the infrared wavelengths, as well as the chromospheric network and so forth, which show up in say hydrogen alpha or calcium K-line. And so this is an ongoing project at the observatory. We've been working on this instrument for a couple years now, and it's been quite a challenge. Yeah.
Before you put the new larger solar, telescope in, you used to give tours in the summer on the weekends. We were told that that wouldn't happen because of the tight space. I thought I had just read recently that there might be a limited opportunity to take a tour of the observatory.
Okay, at this point, I'm not quite sure how that's going to work out yet.
You might mention the Starlight Festival and the tours associated with that.
Oh, well, that's true. There will be this big event that's going to be taking place in Big Bear over Memorial Day weekend. It's called the Starlight Festival. And you might have heard about it because it was just talked about in the Grizzly this week, where they have gotten permission to close down the Village Drive during the event. And what that's going to involve is a large number of organizations that are going to be displaying things in the village. And also, we're going to be scheduling some special tours that are going to be done through that Starlight Festival. As you mentioned, the space that we now have in the building, because of all of the expansion of the instruments, is quite tight, and so we're quite limited as to the number of people we can handle in tours, but we will be planning to do that. Any other questions? Yeah.
Do you ever run a live feed or something through the college or someplace that we could go and watch? I looked at the website and seen the still photos, but is there something more of a
Well,
live feed or?
well, what we do have is that we may be developing something like that in association with the Starlight Festival. I don't know exactly how that's going to work yet, but that is one of the things we're talking about. But what we do have right now on the website is there is a live H alpha full disk feed. We have a small telescope that's next to the big one. You might remember that on the old telescope we had this full disk hydrogen alpha telescope, which we used for flare patrol and for also finding interesting places on the sun to observe. There wasn't any place to put that on the new telescope. What we ended up doing was putting a version of that telescope in this small dome that's next to our big one on the causeway. And we do have a live feed from that updates every minute.
Okay.
What is your website?
Our website is www.bbso.njit.edu, which I know sounds kind of long, but if you Google BBSO, you'll find it. And so yes, this is what one of our full disk images looks like.
Do you still operate the Earthlight telescope as well over there?
We do have another project at the observatory, what we call Earthshine. And what that is, we can use a small telescope to measure the amount of light that's reflected from the Earth to the Moon and back. And the purpose of that is not really to study the Moon. The purpose of that is to study the reflectivity of the Earth, which can change depending on the amount of cloud cover and so forth from weather systems. And so we're monitoring that Earthshine over time using a second telescope that's actually located in the same dome as the Hydrogen Alpha telescope. So during the daytime we operate the Hydrogen Alpha telescope, and at nighttime, in the right phase of the Moon, we operate the Earthshine telescope. That's the only telescope we have that operates at night. Yeah?
John, personally, I do monitor that site for the full.
Mm-hmm.
For the full.
Yes.
And it's an extension of the one you just gave on the site that you just.
Yeah, it's.
And I think the interesting thing of it is that it's updated every minute.
Mm-hmm.
So that every minute you can observe, if you carefully monitor it, you can see the changes that occur on the sun, on the surface of the sun.
Oh yes, it's been especially interesting this week because there's a very nice active region on the disk right now.
Yeah.
Mm-hmm. Yeah.
Are you or your group involved with the STEM program at the middle school in Arbaugh?
We have some limited involvement with that. We've had the students come to the observatory and see the operation, and also on certain occasions I've been over there to I have a small portable telescope and we can show them the sun that way as well. Yeah.
With regard to that site and the update every minute,
Mm-hmm.
has there been any consideration of just having a monitor for that here at the Discovery Center?
We are working on a new display that's going to be at the Discovery Center. Exactly how that's going to work is not clear, but certainly one of the things that we would be displaying on that might very well be that image.
As well as the virtual tour we're going to be playing on that.
Oh, well, yeah, Erica's reminding me that one of the other things we're planning to have on this monitor that will be here at the Discovery Center will be a virtual tour of the observatory, so you'll be able to see what the inside is like. But exactly how all that's going to work, we're not has yet to be
We're just
nailed
getting that
down.
started, so it's in the early phases.
Okay, thank you. Again, I'd like to thank you all for coming, and again, in response to the question about can we set up live feeds, as I said, John wears a lot of hats at the observatory. That sort of thing is on his list, but we keep piling more on top of it. It's a very limited staff, so please be patient with that. Also, keep in mind there are a couple more lectures coming up. The next ones aren't scheduled until April. Jeff Kuhn
will be here, yeah.
He's a very well-known astronomer from Hawaii who will be speaking on the Colossus telescope project. This is a concept, an extremely large telescope, well larger than any telescope currently in the plan, and how that can be used for the search for extraterrestrial intelligence. A couple of weeks later, we're very fortunate to have Jan Stenflo, another very well-respected solar astronomer, will be speaking on solar magnetism. So watch for announcements like that. And again, if you have any interest in the Friends of the Big Bear Observatory Club, for lack of a better term, please see Eric at the back of the room. Thank you again.
Thank you.
Dr. Varsik, thank you very much. That was enjoyable. I learned a lot. Beautiful facility. Look forward to learning more.
All right, so it's one of the more unusual things about Big Bear.
Well, you know, we played the golf ball for a long time. And I always wondered what it was.
Yeah.
Noticed that it was always open during the day, and then someone said, oh, the solar telescope. Fix that. Wouldn't it burn up? No.
Oh, we've had to deal very carefully with that.
Right. Well, don't look at it.
It turns out that the solar telescope of that type that we have also makes a good solar furnace. And so what we have to do is that, you know, the first focus of the telescope, which is up at the top of the number 2, you know, the image of the sun is about this big at that point.
Right.
And it has about 2 kilowatts of power in it. Okay. And so if it sits on this mirror for any length of time, the mirror will melt.
Yes.
So the mirror behind it has a cooling system to keep it at the same temperature as everything else. And so most of the light, so all the light from the